In today's video, we're going behind the scenes of massive petrochemical refineries to explore the industrial methods of preparation, how we crack larger molecules to create these high-energy double bonds. Ever wonder how we turn thick, sluggish crude oil into the high-octane fuel in your tank or the plastic in your phone? It's all about one massive chemical snap we call cracking. Think of it like taking a long, tangled piece of spaghetti and breaking it into bite-sized, useful pieces. In the industry, we call this the Great Crack-Up. The basics of cracking. Crude oil is mostly long-chain hydrocarbons, big molecules that don't burn very well. To make them useful, we have to break those heavy chains into smaller, lighter molecules. This process doesn't just give us smaller fuels, it creates alkenes, the unsaturated superstars of the chemical world. Method 1: Steam cracking. First up, look at the left side of your screen, steam cracking. This is the brute force method. We take those hydrocarbon chains, mix them with steam, and crank the heat up to a blistering 800 degrees Celsius to 900 degrees Celsius. At these extreme temperatures, the molecules vibrate so violently they literally tear apart. This method is the champion of producing ethene. If you're looking at a plastic water bottle right now, it likely started its life right here in a steam cracker. Method 2: Fluid catalytic cracking, FCC. Now, look to the right. This is the smart way, fluid catalytic cracking, or FCC. Instead of using raw heat, we use a catalyst, usually a powder called zeolite. Think of the catalyst like a pair of chemical scissors. Because the catalyst helps cut the bonds, we don't need as much heat, only about 500 degrees Celsius. This process is the gold standard for producing high-quality gasoline and propane. Propane is the backbone of the massive plastics industry, used for everything from car bumpers to medical syringes. Let's see why alkenes matter. So, why do we care about these broken pieces? It's because alkenes have that special carbon-to-carbon double bond. That bond is like a chemical hook, making them incredibly reactive. Polymerization. We can link thousands of ethene molecules together to make polyethylene, the most common plastic on Earth. Ethanol production. By adding water to ethene, we get industrial alcohol. Synthetic materials. From polyester clothes to the soles of your sneakers, none of it exists without the alkenes produced in these towers. Think of a chemical bond like a handshake. Most molecules use a single grip, but alkenes? They go for the double-handed lock. This is the carbon-to-carbon double bond, the powerhouse behind everything from your morning coffee cup to the fuel in a jet engine. Let's look under the hood at why this bond is a total game changer. Look at the ethene molecule in the center. That double connection between the two carbons isn't just twice as much of the same thing. It's actually made of two very different types of bonds. The sigma bond, this is the strong, stable foundation right in the middle. It's the primary handshake. The pi bond, this is the cloud of electrons floating above and below the center. It's much weaker and more exposed, making it the perfect target for other chemicals to attack. This pi bond is exactly why alkenes are so much more reactive than their single-bonded cousins, the alkanes. Let's see the physical profile. Because there are two bonds pulling those atoms together, the geometry changes. Shorter and stronger. A double bond is shorter than a single bond, pulling the carbons into a tight embrace. The flat zone. Notice the bond angles. At 120 degrees, the molecule is locked into a flat, planar shape. Unlike single bonds, this double bond cannot rotate. It's rigid, which gives the materials made from it specific, predictable strengths. Why it matters. So, what's the so what here? 1. High reactivity. Because that pi bond is sticky and easy to break, these molecules are ready to react at a moment's notice. They are the high-energy athletes of the chemical world. 2. Industrial heavyweight. This reactivity is the secret to polymerization. We can pop that double bond open and use it as a hook to link thousands of molecules together. This is how we create polyethylene, the most common plastic on the planet. If alkenes were a professional sports team, they'd be the heavy hitters. These molecules are the fundamental building blocks of modern life. Because of that reactive double bond we've talked about, we can transform them into almost anything. Let's look at the three big plays they make in the industrial world. Polymerization, the plastic revolution. First up, the heavyweight champion, polymerization. This is the process that gave us the plastic age. Inside a high-pressure reactor, we take a gas like ethene and subject it to extreme force and specific catalysts. The double bonds pop open and act like molecular hooks, linking thousands of ethene units together into a massive chain. The result? Polyethylene. From the grocery bags in your kitchen to the shampoo bottles in your shower, polymerization is the engine of the global plastics industry. Let's see hydration making alcohol. Next, we have hydration. This isn't about drinking water, it's about adding it. By reacting ethene with steam over a phosphoric acid catalyst at about 300 degrees Celsius, we perform a neat chemical trick. The water molecule, $H_20, splits and attaches across that double bond, turning ethene into ethanol, $CH_3CH_20H. This isn't just for beverages. Industrial ethanol is a critical solvent and the base for the disinfectants and hand sanitizers that keep our world clean. Let's move to alkylation high-octane fuel. Finally, let's talk power, alkylation. If you've ever seen premium or high-octane at the gas pump, you're looking at the work of alkylation. In this reactor, we combine alkenes like propene with isoparaffins. This creates alkylate, like isooctane. These are high-energy, branched molecules that burn much more smoothly than regular fuel. It's the secret sauce for aviation fuel and high-performance car engines, ensuring they run efficiently without knocking. Whether it's the bottle in your hand, the sanitizer on your desk, or the fuel in a jet engine overhead, alkenes are the invisible force behind it all. They truly are the heavy hitters of chemistry. Without alkenes, our modern lifestyle would literally fall apart. They are the bridge between raw fossil fuels and the complex materials we use every day. If you found this helpful, hit that like button and subscribe for more pharmacy and chemistry tutorials. See you in the next video. Happy learning!